Definitely run out of the here. So far what we are seeing over it now, we have discussed about them, how to design a FAR filter using Hamming window. Hamming window. So today what we are going to say, we are going to continue the same problem. The thing has to be that hd of theta j omega, which is equivalent to 1 for the value of pi by 2 to the pi, and otherwise the value will be equivalent to 0. So we know that the function for Hamming window is equivalent to 0.54 plus 0.46 cos 2 pi by m minus 1 for the limit varying from m minus 1 by 2 to m minus 1. So since we are having the value of m to be the order of the filter to be an 11, so we will be getting of an 11 minus 1 by 2, so 10 by 3. So the order will be given for the minus 5 to 5. So we'll be having the expression of an Hamming window function WHM of n is equivalent to 0.54 plus 0.46 cos, there is 2 pi by m minus 1. So we'll be getting of an pi by 5. So otherwise the value will be equivalent to 0. So let we are doing of an, we'll be finding the value over here. So what is the value of an 0? What is the value of an 1? What is the value of 2? What is the value of 3? What is the value of 4? And what is the value of 5? We have to replace the value of n is equivalent to 0, 1, 2, 3, 4, and 5. And since the limit varying from minus 5 to 5, so the positive and negative values are to be the same one. So we'll be carrying out over on a 1 and minus 1, 2 and minus 2, 3 and minus 3, 4 and minus 4, and 5 and minus 5. So what we'll be getting over that? So we'll be getting the value of 1. For 1, the value to be equivalent to 0.91. For 2, 0.268. For 3, 0.329. 4, 0.8167. 0.5, 0.0018. So that is the first step. Second step, what we should do it of, we have to find out the coefficients using Hamming window sequences. So the coefficients notation, we know that h of n, this should be equivalent to hd of n, that is the value of an Hamming window into our windowing function w of n. So that value is varying from minus 5 to 5. So already we have found out the value of an hd of n is starts from 0 to 5. So that has to be multiplied with the Hamming window function. So let me do over on it and let me find the value of an h of 0, h of 1, h of 2, h of 3, h of 4, and h of 5. So let me multiply over that, and we found out that hd of 0 is equivalent to 1, hd of 1 is equivalent to minus 0.225, hd of 2 is equivalent to minus 0.515, hd of 3 is equivalent to minus 0.007, and hd of 4 is equivalent to 0.5, and hd of 5 is equivalent to minus 0.0475. So that will be multiplying with the windowing function what we got over on it. So we'll get the values to be 0.7 minus 0.205 minus 0.108 minus 0.04 and 0.3 0.0036. Okay. So the next thing we are in need to find the transfer function of the filter. So we know the transfer function of the filter is to be that h of z is equivalent to h of 0 summation plus summation m minus 1 by 2 divided to m minus 1 by 2 h of n z bar minus 1 minus n plus z bar n. So since we will be having varying from m minus 1 to 0 to 5, so we will be having of h of n z bar minus 1 plus 1, h of 2 z bar minus 2 plus 2, h of 3 z bar minus 3 plus z bar 3 plus h of 4 and h of 5. So let me substitute the value of n, h of 1, h of 2, h of 3 and h of 4 and h of 5. So this is the transfer function of the filter. The next step, we are need to find the value of an transfer function of the realizable filter. So which is equivalent to z bar minus m minus 1 by 2 into h of z. So let me do over that z bar minus m minus 1 by 2 into h of z. So we will be getting the value of an z bar minus 5, then z bar minus 1. Then that is z bar 1. Then we'll be having of z bar minus 2, z bar 2, z bar minus 3 and z bar 3. So the final filter coefficients of Gaussian filter, we can able to obtain that h of 0 is equivalent to h of 10 value is equivalent to 0.0036, h of 1 and h of 9 ought to be 0, h of 2 and h of 8 to be minus 0.03, h of 3 and h of 7 to be minus 0.1084, h of 4 and h of 6 to be minus 0.2052, and h of 5 is equivalent to 0.75. So we will be finding the value of an real part and imaginary part. We know that the equation is equivalent to summation is equal to 0 to m minus 1 A of n into cos omega. So let us up to the value of n is equal to 0, 1, 2, 3, 4, and 5. So we'll be getting of an h of m minus 1 by 2, h of 2 h of m minus 1 by 2 minus n. So the value will be getting over that to be h of 5 minus n. So we'll be getting of 0.75. So this will be continuing. The thing is to be that, so we'll be finding value of an, we can able to find the value of an magnitude and the imaginary term with the help of an h of e power j omega is equivalent to 0.75 minus 0.4104 cos per omega cos omega minus 0.2168 cos 2 omega minus 0.063 cos 3 omega plus 0.072 cos 5 omega. Okay, so let me have this into the homework one. Design a filter with HT of e power j omega for n is equivalent to 7 using Hamming and Hanning window. Similarly, HT of e power j omega is equivalent to e power minus j 5 omega using a Hamming and Hanning window with n is equivalent to 11. Okay, and then design FAR filter response with the Hamming window with n is equivalent to 7. Okay, so now let me see the next column. For a FIR linear phase digital filter approximating the ideal frequency response, HD of e power j omega is equivalent to 1. The value omega is less than or equivalent to 5 by 6. So the otherwise the value will be equivalent to 0. So we are determining the coefficients of a 5-cap filter using rectangular window. Okay, so here the omega c is equivalent to 5 by 6. So automatically the value of n and then n value is given as an 5. The first step we have to find out the filter coefficient. We know that hd of n is equivalent to 1 by 2 pi integration of minus pi to pi h of e power j omega e power j omega minus d omega into d omega. So 1 by 2 pi integral minus pi to pi e power j omega into d omega. So when we are integrating this, we'll be getting of an sine of n minus alpha omega c into sine of pi minus n minus alpha omega. Okay, then we'll be seeing over that. So hd of n is equivalent to sine pi by 6 n by 5. So the limit varying from minus 2 to 2. So let me find the value of an 0. So hd of 0 is equivalent to sine pi by 6 of 0, pi by of 0. So we'll be making of 1 by 6. So sine the value will be, so we'll be getting of an 1 by 6 nothing but an 0.16. So we'll be applying limit theta by theta is equivalent to sine theta by theta. The value is equivalent to 1. We will be using LHC rule. Similarly, for n is equivalent to n, hd of 1 and hd of minus n. So we'll be getting of an 0.5 divided by 5, which is equivalent to 0.159. For n is equivalent to 2, we'll be getting of an 0.1379. The second step, we are in need to find the value of a rectangular window. We know that the value of rectangular window is equivalent to 1 for the limit varying from minus m minus 1 by 2 to m minus 1 by 2. Otherwise, the value will be equivalent to 0. So the value will be for the value of minus 2 to 2, the value is equivalent to 1. So we'll be having the rectangular value to be 1. So what's the value of hd of 0? That has to multiply with the value of an 1. That will be the third step. In the case of an fourth step, we have to find out the transfer function of the filter. So we know that h of z is equivalent to h of 0 plus summation n is equivalent to 1 to m minus 1 by 2 h of n z power n plus z power minus n. So let me do over on it 0.5 plus h of 1 z power minus 1 plus 1 plus h of 2 into z power 2 plus z power minus 2. So substitute over on it. Then the next step to be we have to find out the transfer function of realizable filter. So h inverse of z is equivalent to, that is h dash of z is equivalent to z power m minus m minus 1 by 2 into h of z. So that we can able to obtain the, after substituting the values of over on it, we can able to obtain the filter coefficients of partial filter are given as h of 0 is equivalent to h of 4 is equivalent to 0.137, h of 1 and h of 3 are to be 0.9, h of 2 and h of 5 to be h of to be 0.16, and h of 5 to be 0. So after that, we know that we have to find out the real value and the imaginary value. So a of 0 is equivalent to h of m minus 1 by 2 and a of n is equivalent to 2h of m minus 1 by 2 minus n. So we can able to find the value of 1 and 2 and we'll be finding the value of an phase filter. So this is the way to complete all your windowing functions. So the thing has to be that we have to find out the transfer function. Second step, we have to using what window they have given. So then third step, we have to multiply the windowing function and the impulse response function. Fourth step, we have to find out the transfer function of the filter. Fifth step, we have to find out the transfer function of realizable filter. And the last step to be, we have to find out the real part value and the imaginary part value. Okay, so the thing has to be done. So we have to design one more example. Design an ideal bandpass filter with a frequency response HD of e power j omega is equivalent to 1 for the value of varying from pi by 4 to 3 pi by 4. So for the given value, n is equivalent to 11. So we can show that cutoff frequency, two values are given, one to be pi by 4, another one to be 3 pi by 4. So we'll be using the formula of an HD of n, 1 by pi n minus alpha sin omega c2 n minus alpha minus sin omega c1 n minus alpha for n is not equivalent to alpha. So for n is equal to 0, so find the value of an HD of 0, 1, 2, 3, 4, and 5. The next step, we know that we have to use the rectangular window. So we know the rectangular window will be equals to 1. Third step, we will be finding the filter coefficient using rectangular window. And the fourth step, we have to find out the transfer function of the filter. And the fifth step, we will be finding the transfer function of the realizable filter. And finally, we will be finding out one your real values and the imaginary values. Okay, so this is the way to proceed your windowing function. Okay, so the remaining things we can see in the next class. Thank you.